Hello everyone, today I want to share the paper review of kernels and regularization on graphs. This paper mainly introduced a family of kernels on graphs based on the notion of regularization operators, and developed the regularization theory of learning on graphs using kernel. What's more, it explored methods for efficiently computing and approximating kernel metrics. However, because of the limited time, I won't go too deep on this paper, but reveal the useful part based on my research. And I will mainly review two parts: the basic definition on graphs and what's doing when applying regulations on graphs. At first, let's have a basic review on graphs. Here, what we focus is undirected unweighted graphs. There are two basic metrics to describe the graph's property or topology, where adjacent matrix is used to indicate the connectivity of a graph, and the degree matrix can show the one-hoop neighborhood of each vertex explicitly. Then, based on these two metrics, here comes the critical definition: the graph Laplacian and normalized graph Laplacian. Here is the formula to calculate them. These two metrics are foundation of spectral graph theory, and there are two well-known theorems of them. Normalized graph Laplacian is a symmetric, positive, semi-definite matrix, and its eigenvalues satisfy this condition, which is important when apply the graph Laplacian on regulation. Another theorem is that if graph is regular graph of degree d, then normalized graph Laplacian or graph Laplacian as well as adjacent matrix share same eigenvectors. Intuitively, graph Laplacian and normalized graph Laplacian can act as linear operators on function or vector. That is, if function or vector f is defined on graph, for example, if the element of the function or vector f is correspond to the vertex on each graph or on each vertex in the graph, fa correspond to a, fb correspond to b, then we can have the norm of graph Laplacian on S, which can be calculated in this. Thus, the semi-norm on F by graph Laplacian penalizes changes on adjacent vertex. This means that I is adjacent to J, and this means there are changes between the two vertices. And in this way, the regularization can be applied. Before we go deep into regularization via graph Laplacian, we first have a brief review on regularization operators. Now we begin with the familiar Laplacian operators, and to see what's the relationship between this operator with the form of regularization. At first, we will see this definition. Here, the triangle is the familiar regularization operators, and this is the Fourier transform of a function f. This is a function that penalizes frequency confidence of f of this Fourier transform. It should be noted that the pair of phi and lambda is the eigensector of the Laplacian operator, because when you apply the minus Laplacian on the base of the Fourier transform, you can get this, and with a little bit simplification, you can get this result. Now you can easily find it is very similar to the traditional solutions to find the eigenvalue or eigenvector for matrix. That's where the eigenvalue and eigenvector show up. So this can be regarded as the eigensystem of an operator. Now let's turn back to this formula which appeared on this
As you can see, this is the function multiplied with one of the eigenvector of the eigensystem. It means that we shift the information based on eigenvector by shifting the organelle ones. And this means that we patternize the information according to the eigenvalue. Thus, we select the information that corresponds to the eigenvector and use this function to patternize the information to pay attention to the information that it has a similar direction with the eigenvector. Up to now, we can find that there is a mystery part of this formula. That's R. What we define R determines what is the regularization of F. That means that the construction of R has relationship with the regularization form. And let's have a look with an example. So if we let the R applied on the Laplacian operator equals to this result, then from this formula we can easily replace the operator with the eigenvalue, because when we apply the R to the Laplacian operator, that means that we apply the R to eigenvalue in this formula. So we get this result. And as what I mentioned before, the phi is the eigenvector, can be regarded as the eigenvector of the traditional Laplacian operator. Thus, this phi equals to this, which is the basics of Fourier transform. What's more, by replace this into this part of the formula, we can get this, and this is the Fourier transform. There is the traditional Fourier transform, and we can simplify it to this, which you can find like this. It's a little bit straightforward, right? Then we focus on this. This is the eigenvalue of the Laplacian operator, and when we use this formula, we can see that this eigenvalue equals to this. Thus, we use this to replace this element, and use Taylor series to have a deep simplification, and we get this. Now we can say that if we divide R in this form, we can get this result with this formula. So it means that such definition of R leads to Gaussian IBF kernel on regularization. So we can find that the definition of R has a close relationship with the regularization form, and so we can pay attention to what to choose the R to decide the regularization form that we want to achieve. Now we can come to the regularization on graphs. According to what I mentioned before, similarly to this, we can find that the regularization function on graph can be defined as this. You can see we borrow the definition of this formula to define the regularization on graphs. And also with similar method, we can find that we apply R on the graph on the normalized graph Laplacian, and it means that we apply R on the eigenvalue of the normalized graph Laplacian, and in this formula. So the choice of R determines how we regularize the function defined on graph. And what's more, small eigenvalues of the graph Laplacian have associated eigenvectors which vary little between adjacent vertices. So when we want to define the regularization on graph, we may simply do the eigenfactorization on normalized graph Laplacian, and then we apply some functions on its eigenvalue. And if we calculate this, we can do the regularization of F on graph. Thank you for your attention.